Us today about the research. Thank you for doing that. Looking at bridging scales in ocean models.
Okay, thanks for the great introduction. So yes, exactly. Welcome to today's ICCS seminar. My name is David. I work at ICCS now, but yeah, today will be only about stuff that I did at Sorbonne University, where I did my PhD about bridging scales in ocean models on data-driven parameterizations of mesoscale eddies. And so I wasn't quite sure what is the audience today, so I think I left quite some space for introduction for those of you who are quite new to eddies and parameterizations and ocean modeling in general. And so what I want to quickly start with is how do mesoscale eddies look like? So here I brought you one snapshot from NASA, which shows you the surface currents in our oceans, and there you can see two important features. So one is this strong belt of a current going around Antarctica. So that's the Antarctic circumpolar current. But you can also see that it's not a laminar flow. If we activate the animation, then you can see it's really consistent of many vortices and meandering patterns. So these are the mesoscale eddies we're talking about, and they have scales of from roughly few 10 kilometers to hundreds of kilometers and live for a couple of months. So they can really cross entire basins, and they're mainly found in regions, they're found everywhere, but mainly in very energetic regions, like the Gulf Stream region. And I think most of you have heard about the Gulf Stream. It's responsible for the warm weather we have here in the UK. And again, as you can see, it's not a laminar flow transporting warm water to Europe, but it's patches up in all these vortices. And this is what I'm gonna talk about today. How do we model this in ocean models? And this brings me to the problem, which is the problem of scales in ocean modeling. And that problem is that we try to simulate processes that range really from millimeter scale to 10,000s of kilometers, so to global scales, and also from a temporal scale from seconds to millennia. So there's always this trade-off between what can we actually resolve in the models and what can we not resolve. So there's always a resolved part and an unresolved part. In terms of horizontal resolution, one example for a grid that we use in climate model is this one. So that's the NEMO grid. And as you can imagine, so we split up our ocean in these grid boxes, and everything that is smaller than the grid box cannot be resolved. And to tie this issue with mesoscale eddies now, so the typical length scale of mesoscale eddies, you can see here, it's linked to the Rossby radius of deformation and is linked to the stratification, so the vertical gradient of density and the Coriolis parameter. And with this, we can ask the question kind of the other way around. We can ask which horizontal resolution would we need to represent mesoscale eddies? And there, Hallberg et al., they came up with this map where you can see that around the equator, roughly a horizontal resolution of 1 degree latitude longitude can be enough to represent mesoscale eddies. But if you go to higher latitudes and less stratified fluids, you need higher and higher horizontal resolution. And to give you some context, so the last CMIP exercise informing the IPCC report, the CMIP 6 models, they had an average horizontal grid size of 70 kilometers, which is in this regime where eddies are not resolved explicitly almost anywhere. And for the first time, they moved into this phase of high resolution model intercomparison project, where they moved to a horizontal grid spacing with an average of 20 kilometers. And so the bottom line here is that in current climate models, mesoscale eddies can only be partially resolved, and they need to be parameterized. And this map also helps us to classify different kinds of ocean models. So we have on the far left side, we have the eddy parameterizing regime, where, as I said, almost all of mesoscale eddies needs to be parameterized. They are not explicitly resolved. On the other side, you have the regime where they are explicitly resolved. And then we are slowly moving into this gray zone in the middle, which is the eddy permitting regime, where eddies are partially resolved, but not everywhere. And this is what we're going to focus on today, finding how can we parameterize eddies in this regime. And for a quick introduction, I also want to highlight what is the role of eddies in the climate system. And the dominant role, I mean, they have a huge role, but one of them is linked tightly to the energy cycle. So they link energy at a various range of scales, from large scales to small scales, hence the title bridging scales. And so where does the energy come from in the oceans? Mainly from the surface, coming from solar radiation, wind forcing, buoyancy fluxes, etc., and mainly at larger scales. And then how does this energy now get to the smaller scales? So first of all, the surface forcing, it sustains a reservoir of available potential energy. So this is potential energy, which, as the name says, it's available because through this buoyancy fluxes and surface forcings, you basically lift heavier water. So this is a layer of stratified fluid. So you have lighter water above denser water. And if you, with this surface forcing, you can raise the potential energy by sloping these isopycnals. And it's available because you can flatten these isopycnals to extract this potential energy. And now, one important role of eddies is to transfer this energy towards smaller scales, towards dissipation. And this happens through turbulent scale-scale interactions, and one important role of turbulence in general. And then in the mesoscale, more particularly at the scale of the Rossby radius of deformation, where eddies are formed, this available potential energy is extracted through baroclinic instabilities and forces the eddy field. So it gets transformed to eddy kinetic energy. And now in two-dimensional fluids or very stratified fluids like the oceans, there's also an inverse direction. So this eddy kinetic energy can actually cascade upward, upscale towards the larger scales again. And so this is a very introduction to energy transfers in turbulence. But I also want to link this again to what we've seen before. So in the eddy resolving regime, where we say that eddies are explicitly resolved, there's still some part of this dissipation missing, which is why we still need some parameterizations, like there's this Magorinsky scheme that you can see here, for example, which is responsible for this forward cascade, this dissipation of energy. Then if you go to the larger scales, you have, for example, the Genten-McWilliams parameterization, which is activated in all climate models, and its main purpose is to flatten these isopycnal surfaces to extract available potential energy. And for this inverse cascade, we have backscatter schemes. So for example, the one by Janssen and Held, introduced in 2014, which are responsible for this upscale transfer of kinetic energy. And again, this is what we're going to focus on today. But now, so this was kind of needed introduction to what we're after with the parameterizations. But now I want to make it a bit more clear what could be one effect for the climate system. And one effect is it has a strong effect on the ACC, the Antarctic Circumpolar Current, that we have introduced before. So the Antarctic Circumpolar Current, as I mentioned, it's the world's strongest ocean current with 170 Sverdrup, so 170 million cubic meters per second. So that's a lot of water that is being moved. And the important part is also that it's connected to all major ocean basins, which makes it really crucial in the exchange of heat, carbon, nutrients, and basically any property across the globe. And this makes it really important to get the ACC right in our climate models. And one important part about this current is also that it's approximately in thermal wind balance, meaning that the strength of this current is linked to the isopycnal slope. It's basically proportional to the isopycnal slope. And how you can imagine this is if you take a cross section through the Atlantic, which you can see here, and we look at the density profiles that you see depicted, then you can see that they kind of outcrop towards the Southern Ocean. So the buoyancy fluxes and the wind, they sustain the store of available potential energy of dense water close to the surface, and sustain the store of available potential energy. And as we have learned in the slide before, eddies extract this available potential energy and flatten the isopycnal surfaces. And thereby, eddies are really crucial in controlling the strength of the ACC and therefore also the global stratification, but also the global transports and the transport throughout all ocean basins. Just to give you a motivation on why it really matters to represent eddies well in ocean models, and to show you how this can also go wrong, I brought you this figure by Hewitt et al. From 2020, which shows you all the CMIP, the models that went into the CMIP6 intercomparison project, so that went into the IPCC report. And what you can see on the y-axis is the ACC transport for all of these models, and the x-axis is the horizontal resolution of the model of the ocean grid. And in the gray bar is what we kind of know from observations. And what you can see here is that there's this clustering of the horizontal resolutions, and especially in the eddy permitting regime, so in the middle where we are not, so on the left-hand side, that's the eddy parameterizing regime that we've seen before. On the right-hand side is the high-resolution models, and then in the middle, that's the eddy permitting regime. And particularly there, we are quite unsure which processes of eddies need to be parameterized and which don't, which leads to strong uncertainties and biases in current ocean models due to this representation of eddies. And this has been acknowledged, and there's many groups working on this issue. And in the last years, there have been more and more publications that target this issue using data-driven methods to try and learn these parameterizations from data. And this is what I want to show you in the last introductory slide, how can this work? So what we need for these data-driven eddy parameterizations, we start with a high-resolution data set. This could be observations. In our case, it's high-resolution model data. And then you coarse grain this high-resolution data to the target resolution of your coarse ocean model. And while doing so, you can directly diagnose the subgrid momentum fluxes that are missing in the low-resolution model. And what previous authors then have done is that they have trained a machine learning algorithm to make predictions of the subgrid momentum fluxes based on the coarse-grained velocities. And so these machine learning algorithms, they make predictions. They can be very bad predictions, but then you can define the loss function. You can iteratively train them on more and more data to make better and better predictions. And once you're happy with the predictions, you can plug them back in the coarse ocean model and hope that the coarse ocean model behaves similarly to the high resolution models where eddies are explicitly resolved. This kind of concludes now the introduction. So now let's come to the questions that we have looked at, or that I will talk about today at least, regarding data-driven parameterizations of mesoscale eddies. So the first one is, how can we deploy machine learning methods in ocean models? So this is both from software side, but also theory side, can be tricky. And how can we quantify potential improvements? As I mentioned, it's quite difficult to get good metrics right, since we know that most of our models are biased in this regard, and we have only very sparse observations. So benchmarks are really crucial for these methods. And finally, we also want to look into the actual assessment of these parameterizations and see how do they compare, how do they perform, in particular compared to a first principle-based approach, so a backscatter parameterization that was already available to us. And we're going to start with the first part, building a benchmark. So how can we quantify potential improvements? And for this, I introduced a new configuration, which is the Dino configuration that you can see here. It's implemented in NEMO as well and stands for Diabatic Never World Ocean. But what is important here, it's an intermediate complexity model. So intermediate complexity meaning, as you can see, the bathymetry is quite idealized. However, we can capture essential aspects of the global ocean circulation, such as, for example, equatorial dynamics, the polar, subtropical gyres, subpolar gyres, the western boundary currents, but also, as I mentioned, the ACC, the Arctic Circumpolar Current, and the dense water formations associated with all these. And the idea is that the modeled physics are similar to the ones in like in real climate models or the ocean component in climate models, but it comes at a fraction of the computational cost. And this allows us to run the Dino configuration at 1 degree, quarter of a degree, and 1/16 of a degree horizontal resolution, so spanning this entire range of eddy parameterizing to eddy resolving regime. And so then we can actually run the simulation at this highest resolution and actually resolve the mesoscale eddies explicitly. I want to spend just 1 minute on this computational cost here, because as you see, so the computational cost still, it's quite expensive. So it scales cubically with the horizontal resolution, the computational cost. So at highest resolution, we still have about 9,000 CPU hours that we need per simulated year. So what does that mean on our machine in France, the Janzé HPC? Means that, first of all, for 100 years of simulation, we would need at highest resolution 900,000 CPU hours, which is quite expensive in terms of energy, in terms of carbon, but also in terms of human time. So you would need to wait for 10 days to get your simulation at reasonable parallelization. But to give you an idea of how this looks in real climate models, so I gave you the same numbers for the IPSL climate model. So this is now including atmosphere, including ice, biogeochemistry, land model, etc. And there you can see that even at low resolution, at 1 degree, it costs about 300,000 CPU hours. So really a big advantage of these idealized models at low resolution, at least. So these numbers were I took from this website where I entered my simulations. And so this was just to make you aware of how useful these idealized configurations are, especially as benchmarks. And we published this in GMD, and it's also used by a couple of other groups. Then how do the simulation results look like? So this is now snapshots of surface kinetic energy for the eddy permitting regime on the left, and then the eddy resolving regime on the right. And what we can do then, as we mentioned, we can coarse grain the high resolution velocity fields to the low resolution and get this picture on the right. And so these are just snapshots, but if we integrate it over time and over the whole spatial domain, then you can see that the high resolution is really about 2.5 times more energetic than the low resolution, because it captures more, just more scales. But even if we coarse grain it to low resolution, it's about twice as energetic, which is precisely linked to this inverse cascade of kinetic energy, because even the larger and resolved scales in the coarse ocean model got energized from these energy transfers. And as I mentioned in the methodology, we can actually diagnose the responsible fluxes directly. And we can have a look on how they look like instantaneously. So there's energy really chaotically injected and taken out of the system at various different scales. And so this is the fluxes that we're actually after in our parameterizations. And just to make this a bit more quantitatively, I will go to spectral space for the Southern Ocean here. So within this box that you can see in the bottom, I can take the Fourier transform, 2D Fourier transform of the kinetic energy, but also of the energy transfers to get these pictures of kinetic energy spectra on top and kinetic energy transfer spectra in the bottom. So for those of you who are not very familiar with it, what the top one gives you is basically the energy, the kinetic energy contained at various length scales. So going from coarse length scales on the left to the smallest length scales on the right. So this is also why the black line, that's the high resolution run, extends further to the right because it resolves smaller scales. But what you can also see is that at all the length scales, the high resolution run is more energetic. And even after coarse graining, at the large scales, most of this kinetic energy is retained. And so this is what we're after, what we're trying to achieve with the coarse models as well. And for this, we need the subgrid fluxes that you can see in the bottom. So again, it's on the x-axis, it's the same axis. So it's the length scale basically from large length scale on the left to smaller scales on the right. And it's the energy transfers so that you can see that the subgrid fluxes, they dissipate energy at small scales, and they backscatter it at the large scales. And so this is also why they're called backscatter parameterizations, and this is what we're after. And yeah, this concludes the metrics that I wanted to show for the benchmark, for the Dino benchmark. Now let's come to the next part, the machine learning methods to parameterize eddies. And I think the best way to start is not to talk about the data-driven methods for now, but first the baseline. So how would we go about this from a first principle-based approach? So the kinetic energy backscatter approach. So as I mentioned, these subgrid momentum fluxes is what we're after. And how this was traditionally done is that you define a budget of subgrid kinetic energy. You define a prognostic equation for it with a source, which comes from a dissipation term, a viscosity term that you introduce, and a sink, which comes from a negative viscosity term, so a backscatter term, negative viscosity term in this case, that you introduce to the model. You can also define some subgrid diffusion, advection. This doesn't matter for the talk today, but there's multiple parameters that you can talk about a lot and tune a lot. But what we're ultimately after is we want one term that dissipates the energy at small scales and one term that energizes the flow at large scales. So that in a net effect, we have an energization of the flow similar to what we've seen in the coarse-grained high resolution. And as I mentioned, this was first published by Janssen and Held in 2014, at least for ocean models, and has been then ever since worked on by multiple groups. One that I want to highlight here is the one by Pavel Peretyugin, because he implemented it for the first time in the NEMO model, which is why I used it in my benchmark, because it was just available. I didn't need to implement it myself. And so now that you've seen what we're trying to parameterize, let's go about the data-driven methods. So again, this is exactly the same schematic that you've seen before. And I now want to go through it for two different parameterizations. So one is the Zanna-Bolton 2020 parameterization, which follows the same schematic. Just you have as high resolution data, they used quite idealized model simulation of a rectangular grid box. And for training a machine learning algorithm, they chose an equation discovery approach. So this is a relevance vector machine where they basically define a set of basis functions that you can see here. And they find, essentially they find a sparse linear combination of all the gradients and products of these terms to find a small enough but descriptive equation to approximate these fluxes. And this is the one they came up with. Again, if it interests you, I wanted to include it, but it's not needed to understand in detail for the talk here. But basically, they found a form of the stress tensor and included the subgrid fluxes as a gradient of that. And then once they found it, you can then integrate it into your ocean model. And there, this method has quite an advantage because it's just an equation. So you can just take it, discretize it on your grid, and make your simulations. Made my life fairly easy. Like you just need to make some choices about discretization, maybe numerical stability, but that's all you need to do. And then also during inference, it's fairly cheap since it's just one equation. One additional equation corresponds to about 100 operations per grid point, which is comparable to other parameterizations in our ocean model as well. So this is one advantage definitely of this method in terms of implementation and inference runtime, computational cost. The kind of complementary approach that I want to introduce today is Guillaumin and Zanna 2021. So again, same schematic, different training data. So in this case, it's global surface data they used. But more importantly, the machine learning algorithm is a different one. So they used a convolutional neural network to make these predictions. In this case, quite a large one, actually, with 10 to the power of 5 trainable weights. And again, once you're happy with your predictions, you have to implement it into your coarse ocean models. And in this case, this is much more tricky because, first of all, this training and these machine learning algorithms are quite optimized and were performed also in Python in this case, but our ocean model that we use, the NEMO model, is written in Fortran, which is not necessarily optimal for machine learning algorithms. And secondly, also during inference, that they choose such a large model means also that they have around 10 to the power 5 operations per grid point. So order like 1,000 times the parameterizations we've seen before. But also this is about 1 order of magnitude more expensive actually than the ocean model itself. So this is definitely a challenge. So how can we implement such a parameterization in NEMO? And the answer is by using the hardware that was designed for these problems. So we managed to run the inference step on a GPU while running the NEMO model simultaneously on a CPU using EOFIS. So it's a package developed by Alexis Barge in Grenoble, who used the OASIS coupler, so the coupler of NEMO to the atmospheric model, the sea ice model, etc., to just pass the velocity fields and the separate fluxes to the neural network to perform the inference. And this was among the first integration of a neural network into NEMO, so quite a win there. And also we achieved a kind of 50-50 in at least wall time of the evaluation of the neural network and the evaluation of the NEMO time step. However, we still ran against some limitations in terms of hardware that I just want to quickly raise. So it's not really hardware, the limitation, it's more the allocation that we had on our machine. So on the Jean Zay machine, typically you reserve 4 GPUs with 40 CPUs. And if you want to have a realistic problem in the NEMO ocean model, so our eddy permitting idealized case, for example, you need about 15 nodes for this realistic problem, which then translates to you need to reserve 60 GPUs for this problem, which is way too much for the inference. And because of NEMO, you need to burn a lot of GPU hours in your allocation, which is why we raised this issue for the need of allocation of few CPUs with a few GPUs with many CPUs. During my time in a PhD, we didn't get anywhere with this, so we had to reduce the problem, meaning we had to run for shorter time, but still we could do the assessment, which will be the last part of this talk. Just to quickly sum up the advantages again and the disadvantages of the two methods. So we looked at the equation discovery approach and the neural network approach. During the training phase, the equation discovery approach is not as advantageous. You need to make many assumptions about the terms that you include. And you need to have a lot of knowledge before you can actually learn this equation. So to be fair, actually, they learned an equation that was already more or less known beforehand. While in the neural network approach, you could potentially really learn new physics. Like you don't need to constrain the model that much. While on the inference side, like once you implement it, definitely the equation discovery approach is advantageous because it's cheaper and more straightforward, while the neural network approach is definitely more challenging. And so now let's look at how these parameterizations perform in our benchmark case. So again, these are the colors for the 3 parameterizations, the neural network approach in blue, then in purple, the equation discovery approach, and the baseline in orange. And without, so again, to remind you, for this metric, our target was to energize the flow comparable to the coarse-grained high-resolution case. And out of the box, so with the default values of the parameterizations, we found that the neural network approach was far too weak. It didn't energize the flow enough. The Zana-Bolton parameterization was slightly too weak, and the backscatter baseline was too strong. However, this is kind of as expected. Like if you introduce a new parameterization, usually what at least ocean modelers do is a tuning phase. So you find the optimum value parameter for your parameterization to target a specific metric, in this case, total kinetic energy. So we found these optimal values in order to make them comparable. So all these parameterizations, they target the same backscatter, the same domain integrated kinetic energy. And still after this tuning, they ran stably for at least these 30 years, but we also tested it for longer. And as you can see here, we can now diagnose directly the subgrid fluxes these parameterizations introduce. So again, on the left is the video you've seen before. This is the target we diagnose from the high resolution. And then next to it, you have the equation discovery approach, the baseline, and the neural network approach. And this is just to show you, again, similarly, they inject energy, they take out energy at various different scales. So this is a good sign, but of course, we want to look at this more quantitatively. So again, we go into spectral space. So this is, again, the kinetic energy transfers over the length scale going from large scales on the left to small scales on the right. And the black curves is the ones that you've seen before. So that's what we diagnose from the high resolution ground truth. And what you can see is that regarding the baseline in orange, we find that in both the Southern Ocean and the Gulf Stream at least, the transfers are shifted slightly towards smaller scales. For the equation discovery approach, the opposite is the case. They are kind of shifted towards larger scales. But yeah, these could be potentially be okay. I mean, they might not perform as well in some regions as in other regions. However, for the neural network approach, we really found a big problem. So in the Southern Ocean, as one example, but also in other regions, it does not energize the flow at all. It even takes out energy at the large scales. And we attributed this first to a bias towards the low latitudes, so that the parameterization towards the equator injects more energy, and it has less and less backscatter towards the high latitudes. And this, again, we attributed to the fact that in the dyno configuration, the model grid, it gets finer and finer with latitude, so in line with the Rossby radius, as we discussed before. But the neural network has no information about it. So the grid information is no input variable to the neural network, so that two neighboring velocity points look the same for the neural network at the equator than at 70 degrees north, even though they are spatially much closer at high latitudes. And this has consequences, since, as I mentioned to you, the Southern Ocean is really crucial. The ACC is crucial, and the representation of eddies in the Southern Ocean is important for the entire Earth system. And I wanted to show you this just with the meridional heat transport. So this is a profile of meridional northward heat transport in petawatt. And again, in black, you can see the high resolution target. Then in dotted black, that's the low resolution, the low resolution reference case. And then you can see that both the parameterization, the Zanna-Bolton, the equation discovery one, and the baseline, they really improve the meridional heat transport, while the neural network approach does not. And we believe this is because of the poor representation of backscatter in the Southern Ocean there, which has links to the isopycnal structure there. And just to conclude this a bit more generally, so we've seen this issue with GZ, that it underestimates kinetic energy at high and overestimates it at low latitudes. You can see this again on the left-hand side plot. So this is again the integrated kinetic energy, but now as a profile of latitude. And you can see in blue that at low latitudes, it's really way too much energy, while at high latitudes, it barely energizes the flow at all. So again, we attribute this to this unawareness of the model grid. But similarly, we found that none of the parameterizations, they perform well in the Gulf Stream region. And again, we believe it's a question of the information the parameterizations were informed about. So we know that for the Gulf Stream, the bathymetry is very, very important for setting the path and also the separation point of the Gulf Stream. So none of these parameterizations are informed about that. And last but not least, also in the depth profiles, if we look into the integrated kinetic energy as a profile of depth, we see that both the data-driven parameterizations, they underestimate the kinetic energy at the surface and overestimate it at depth, which again speaks to the fact that they were trained on data that didn't explicitly include at which level the data was coming from. So this brings me to the take-home messages, to the conclusion. So first, there's many more metrics that I won't show today that you can check out in a paper that got accepted now. It's this is still a link to the preprint, just waiting for the production of the paper. But to quickly conclude, so data-driven parameterizations of mesoscale eddies, they're now possible in NEMO, including a neural network-based approach. So this is the new part. And then the main take-home message I want to stress here is that it's really crucial which data you include in the training data. So you need to be selective. You need to be quite selective about what information you need to provide to the either neural network or the equation discovery approach. So, for example, resolution-dependent information such as the grid, as we discussed, as the bathymetry could also be included explicitly, but also other energy fluxes from different parameterizations would be one idea we would have to include explicitly in the training. And then as a last point, we also found that the equation discovery approach is slightly advantageous over the neural network, also because it's interpretable. So we needed to actually discretize it onto the model grid. So it's grid aware by implementation, basically. So it's therefore better at generalizing to the different model grid, for example, so that we kind of, in this matrix that I showed before about the advantages and disadvantages of more assumptions you need to make during training, but it's cheaper at inference. What we would kind of suggest is that this neural network approach is very good to explore and actually learn potentially new physics. You can just include the bathymetry, the grid as input parameters. Like it's quite straightforward to do. But in the long run, we should potentially also try to find interpretable parameterizations in order to get the benefits in terms of implementation and the runtime and inference. And with this, I just want to thank you for